In this video, we're going to look at how to solve first-order ODEs using exact equations. Now, hopefully you've already seen the video on the theory behind this, because this isn't any theory. This is just pure examples. So let's look at this example. Say we have 4x cubed times y cubed plus 3x squared. That's all dx. Then we have 3x to the fourth y squared plus 6y squared dy. And this is too big for my space, but all of this is going to equal 0. Okay, so all this equals 0. You might say, well, what's the point of doing all these stupid methods? Because remember, there's like this many diffy q's in the world, and we can solve like this many. But that's what this whole class is about, is solving like 1/2 of 1% of a half of a half of a half of a something. But anyway, this is our m, this is our n. It's in the order dx dy. So our first thing is to check if it's exact. Now, if it's exact, m partial y should equal partial n partial x. If it doesn't, then it's not exact and we can't solve it. So that's my first step. So d dy, or partial y, of m is going to be partial y of 4x cubed y cubed plus 3x squared. Now, if I take the partial derivative of that, everything else stays like it's constant except for the y. So that's 12x cubed y squared. There's no y in the second term, so that's going to go to 0. dn dx is partial y of n, which is 3x to the fourth y squared plus 6y squared. So if I act, py. So if I act like everything is constant but the x's, then that's going to be 12x cubed y squared, and there's no x in the second term, so that's going to 0. Now these two are equal, so that means it's exact. Yay! So that means I can actually solve this problem. Now, we know that partial f of no, so we've assumed that there's an answer out there called f. We know that partial f partial x is equal to m. So the idea is that we have two choices. We can either say partial f partial x is equal to m, or partial f partial y is equal to n. And it just depends on which one we think is going to be easier to solve. So we say, is it going to be easier to solve this, 4x cubed y cubed plus 3x squared, or is it going to be easier to solve the other one, which is this? Now, it's really up to you. It's a personal decision. In some problems, it's going to be really obvious that you want to go one way or the other. I'm going to actually do it both ways just to prove that you get the same answer both times. But we're going to go with option 1 first. And we're going to solve this. So this guy's great, but we're going to save him for later. So I'm going to say that df is equal to 4x cubed y cubed plus 3x squared dx. I'm going to integrate both sides. So on the left, I'm going to get f. On the right, I'm going to get x to the fourth y cubed plus x cubed. Now, normally we'd say plus c. But in this case, since we're doing a partial derivative or integral with respect to x, it's not just a constant, but it could be some random function of y. So make sure that you think about that. It's not just c, because it could also be a function of y, because I'm only differentiating or integrating with respect to x. So there could be not just a constant, but a y term in general. Now, my other thing that I know, like we said, is I knew that df dy was equal to this thing over here. And so what I'm going to say is I'm going to say that dy of my thingy that I just came up with, the d dy, the thingy I just came up with, well, that needs to be equal to that 3x to the fourth y squared plus 6y squared. Okay, so I'm not like doing the differentiation here and setting the equal. I'm saying that when I do the differentiation, they should be equal. It's a little bit of a delicate thing, but hopefully you'll figure it out, and we'll do another example here soon anyway. But if I d dy this here on the left, I get 3x to the fourth y squared plus 0 plus h prime of y. That equals 3x to the fourth y squared plus 6y squared. So that means that h prime of y has to be equal to 6y squared, or that h of y is equal to 2y cubed plus c. I've already taken care of the x's, so that's a c. So I can look back at my guess for f. So I have that f is equal to x to the fourth y cubed plus x cubed plus h of y, which is 2y cubed plus c. Now f, I said there is a, whatever you call it, a trivial solution of c. But c of one kind plus c of another kind is still just c in general. So instead of writing it like this, I'm just going to, and from now on, I'm just going to write, so c whatever, I'm going to write it as x to the fourth y cubed plus x cubed plus 2y cubed plus c is equal to 0. And that would be my full solution using the exact method. Kind of makes sense? All right, now because it's very, very similar, I want to solve it again using method 2. So let's pretend that I actually decided that this was a better way to solve it. So I'm going to write it over here just a sec. Okay, so let's say that for some reason I decided that this was going to be a whole lot easier to do. Now it's going to actually be very equivalent, but that's okay. So I have that df is equal to 3x to the 4th y squared plus 6y squared dy. Integrate both sides. Over here on the left I get f, on the right I get x to the 4th y cubed plus 2y cubed, can't spell, 2y cubed plus, now since I'm dy-ing it, I'm integrating with respect to y, that means instead of saying plus c, there may be some unknown function of x, okay? All right, so now I have a guess for f, and I remembered what df dx was. I gotta go pull that one now, actually. Like that. So, I know that if I if I partial x, the f that I just came up with, then I sure as anything better get 4x cubed y cubed plus 3x squared. Those two have to be equal, and that's going to help me find that missing function h of x. It's down so you can still see. So I'm going to ddx this. I've got 4x cubed y cubed plus 0 because there's no x's there, plus h prime of x. That has to equal 4x cubed y cubed plus 3x squared. Now these are going to cancel out, which means that h of x, h prime of x, has to equal 3x squared, which means that h of x has to equal x cubed plus c. Again, combining that with my initial guess for f, that means that my solution is x to the 4th y cubed plus 2y cubed plus x cubed plus c equals 0. And I'll bet you anything, if I zoom out, you're going to see that that's the same answer I got last time. It's just in a different order. So it didn't matter which strategy I used, just sometimes it's more obvious that you're going to go one way instead of going the other way. So again, these are implicit solutions because they're just a lot easier to handle, to do with. A lot of times it's just easier to read. But it's kind of neat. So that's, how you solve stuff with exact equations. I don't know. It's amazing. It's fun. It's what cool kids do. So let me give you one more just to kind of try on your own. Now that you kind of walked through the process. And this is something that's going to take a long time. I'm running through really fast because, quite frankly, I'm sitting here with the solution right in front of me because I'm not stupid. I try not to start videos that I don't already know the answers to, although it happens sometimes. You're going to want to pause the video and go work on this. So say you have e to the x, y times e to the xy, tangent of x, plus e to the xy, secant squared of x. All that is dx. And then you have x e to the xy, tangent x, dy. And now you can't see what I'm doing, but that equals 0. Okay? So you're going to want to pause the video, really spend some time working on this. If you've tried pausing it and didn't get very far, remember that your first step is to identify that this is m and this is n, and that the partial m of y needs to equal the partial n of x, or partial with respect to y of m needs to equal to partial with respect to x of n. I feel like I'm saying it, but I don't know if it's coming out right. In any case, you need to go figure it out. So this is something you want to look at. So again, if you haven't already, pause the video, go see how far you can get. Because if you're just waiting for me to do this in front of you, you're not going to learn it. You really need to spend some time messing around with it on your own. All right, so our first check is we want to check that d dy of m is equal to d dx of n. So d dy of m is this. Y, well, dm is this at least, tan x e x y secant squared of x. All right, so if I d dy this, we'll have to product rule the first part, xy plus x y dxy tan. Man, you can't even see this. It's already kind of crazy. No, heaven forbid I redraw my equal sign. Tan plus x e to the xy secant squared x. Now hopefully the other thing turns out to be something similar. Come here, pencil. You do it. There we go. Sorry, whoa. So now I want a d dx, the other thing, and the other thing was x e to the xy tan x. Okay, if you got stuck here, this is a product rule of 3 things. Don't let this freak you out. Okay, so basically, we'll take an aside over here right quick. If you have the derivative of 3 functions, and we'll just do a regular derivative just so you know there's no funny business going on, of f times g times h, okay? One way that you can think of it is f of g times, or f times g of h. So if I do a product rule, I get f prime times g times h plus f times the derivative of g times h, like that. So that means I have f prime g of h plus f times a quantity. Now d dx of gh is going to be g prime h plus gh prime. So if I distribute that, basically what you get is you get all 3 terms, and I just kind of travel through them, taking the derivatives of them one at a time. So I just have fgh, 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 but first I prime the first one, then I prime the second one, then I prime the third one. And this works for any number of products. So product rule is kind of fun. You just go through all the different combinations of what you're actually going to prime. So assuming you've done that now, or know what we're doing at least, let's go ahead and play around here. So prime the first one is just 1. All right. Prime the second one with respect to x is going to be xy. And then prime the third one. And if I look, those two are the same. So this is an exact equation, so I can use my strategy on it. So maybe you didn't get this far on your own, but maybe you did. If you just wanted to watch the video up to this point, now that you've done this, see if you can tackle the rest. Remember that you want to say, well, I know that I know that partial f, partial x is going to be equal to y e to the xy tangent x plus e to the xy secant squared x. And I also know that partial f partial y of f is equal to x e to the xy tangent x. So it kind of comes down to which of the 2 options do you want to integrate with respect to their whatever respective integrand thingies. So do you want to integrate this with respect to x, or do you want to integrate this with respect to y? Okay, it shouldn't be like that big of a choice. I'm just going to go out and say it. That thing looks hard. The first one looks hard. So I don't want to do that because I'm lazy, so I'm going to go with this guy here. So I have the df is equal to x e to the xy tangent x dy. And I'm going to integrate. Now, f is on the left. Just to make sure you don't freak out, remember that with respect to x, the x and the tangent, the x's are constant, so really I'm just integrating e to the xy dy. Yay. So whenever I do that, I get that f is equal to x tangent x 1 over x e to the xy, right? Because that's what would happen if I take the derivative, I end up with e to the xy. And then plus a function. If you forgot to do that function, make sure that you remember. That's another place where you can go wrong on this, is forgetting to add that function. It's not plus constant, it's plus a function. And luckily, these cancel out. So I have that f is equal to tangent x e to the xy plus some unknown function h of x. Now here's where I'm going to use this guy, is I know that the partial x of my function is going to have to be equal to y to the xy, y times e to the xy, tangent x, plus e to the xy, secant squared x. Like that, those have to be equal. So now I just have to take the derivative of this thingy. So I'll do the tangent first, which is secant squared. Why am I freaking out? Secant squared. Has to be. E to the xy plus y tangent x e to the xy plus the first derivative h equals y e to the xy tan x plus e to the xy secant, I ran off the page again, like that. Now this is kind of fun. Secant squared x e to the xy, secant squared e to the xy, y tangent it. Now the only thing I've got left is actually h prime of x is equal to 0, which means that h of x isn't even a function of x after all, it's just some random constant. So that means that I can come up with my solution, tangent of x times e to the xy plus c equals 0. And that's my final answer to that differential equation. So exact equations, they do feel like a lot of work. They're definitely the problems that you're going to work through and you're going to be like, man, this is just so much time, I just don't know if I want to go through with this. This is probably my least favorite topic in DiffyQ just because there are so many other things that are just way, way cooler. I don't think the other things are easier, I just think they're much more interesting. This just seems like such a special case, but we learn them anyway because it is important to get exposure to them. So all I can say is if you're getting kind of frustrated, just kind of power through. I promise DiffyQ gets better. In a minute, the next thing that we're going to look after this are integrating factors. And integrating factors are what you do whenever you're looking at something and it's not exact, but it's super close. Like say we got here to this point, and this thing was exactly the same thing as this, but this one had like a negative sign in front of it. Is there anything that we can do to possibly set that up, like so we could make them exact after the fact? And that's what integrating factors do. So once you get through exact equations and once you get through integrating factors, then you can get into some of the applications which are pretty cool and some of the more exciting parts of differential equations.